is the state seismologist, Dr. Jake Walters. Jake, how long have you been with the survey? 6 years with the survey. He got his PhD at UC Santa Cruz, and he's going to tell us what we've learned in the last year about seismicity in the state of Oklahoma, which has been a hot topic. So I'm really personally excited to hear this talk and see their findings. Without further ado, Jake Walters.
That's Walter, no S. I'm just teasing you, Carl. Thank you very much. It's wonderful to be here. It's great to have this in person again. I was kind of surprised from Nick's talk earlier to see the sort of roster of OGS employees. And, you know, I've been here 6 years, but based on sort of turnover and retirements, which is a natural progression of things, I find myself one of the sort of, you know, longest tenured kind of employees of the state survey. So it's wonderful to be here in person, and I'd really like to see you all, members of the sort of greater Oklahoma City and Tulsa professional communities, to really, you know, think real long and hard about your relationship with the state survey, and really let's try to forge a lot of these connections. And maybe next year you can encourage some of your colleagues, you can drag them kicking and screaming to this venue again, and we can have, you know, even more fruitful discussions. So I'm going to talk today about some of the sort of things we've learned, and I'm going to sort of, you know, delve a lot into the nature of our mission as a sort of non-regulatory state agency in sort of monitoring the earthquake activity, working closely with folks at the Oklahoma Corporation Commission, who are represented today over here, and how we really ensure that sort of public trust, right? And really sort of keep that sort of, you know, public opinion intact about extracting energy from the subsurface, in spite of what I'll talk about sort of the last decade of seismicity. And really, the only way that we can accomplish this mission is, of course, with that sort of human capital. So a lot of what I'm going to talk about and a lot of what we do is the sort of real-time serving up you know, information within seconds of an earthquake occurring, and that really relies upon some dedicated staff members who you see behind me in those pictures and across the room, of course. So I'm going to talk a little bit about the past, of course, some of the lessons we've learned, you know, how we've navigated this sort of, you know, nexus of induced seismicity in Oklahoma. And really, but also think about the future. So thinking about how you could successfully implement a sort of regional carbon storage program, for example, that would really be impactful for mitigating climate change. So what have we learned in Oklahoma that we can utilize and we can apply that knowledge to the future? So, and I think that's going to entail a lot of things. It's going to be an interdisciplinary enterprise, right? You know, nothing happens in a vacuum or inside a single individual's office. So in order to be successful, I think you need site planning to identify faults in good storage zones. So you need those sort of reservoir engineers, the reservoir experts, the geologists, also thinking about risk and hazard and these kinds of statistics. I think you need to expect that seismicity will occur. We'll hear later from Sherilyn that, you know, the Decatur project produced microseismicity. Now, it never got to the level of an earthquake that was felt by anybody, but in these projects, you should expect seismicity, and maybe I'll talk about some of the things that you can do to mitigate that seismicity. Finally, obviously, I'm a little biased here, but I see a real need to invest in sort of monitoring of the earthquakes, subsurface pressures, and obviously everything that goes into that investment, including hardware, software, people. And then, you know, maybe some strategies to mitigate seismicity when it occurs. Again, based on sort of our role as a state agency. So the last decade in Oklahoma has been somewhat unprecedented, I think, in human history. So this is an example. Here's a plot of all the earthquakes, magnitude 2.5 or greater in our historical catalog, okay? And so in the black, I've sort of labeled these earthquakes different colors. So the black earthquakes are earth seismicity from about 1980 to 2009. And then I switched the color on you around 2009 when we start to see an increase in seismicity across the state. So this is a cumulative plot on the bottom. Yeah, you can see my laser pointer there. And you start to see that the seismicity increases. So how to read this plot is to go from 1980 to 2009, that's relatively flat. So it's somewhat steadily increasing. So there is a background of tectonic seismicity in Oklahoma, but that jumps up significantly starting in 2009 and increases exponentially in the period between about 2013, 2014 into 2019. And then we see this sort of leveling off. So that seismicity rate is somewhat declining over time, but the rate is still much higher than it has been historically, into 2022. And you can see that a lot of the seismicity is clustered in north central Oklahoma, and we'll talk about why that is. There's a broad swath across western Oklahoma, just within driving distance of Oklahoma City, pretty conveniently here. And then, but there is seismicity across the state. So Oklahoma is a tectonically active state. And that's something I try to reinforce in various discussions with agencies around the state and around the nation. Now, a magnitude 2.5 earthquake is something that might be exciting to some folks, right? You're like, oh, whoa, what was that shaking? Was it a truck driving by? No, that was an earthquake. And you can confirm that because our data is offered within seconds. And we're providing those magnitude calculations within seconds in our relationship with USGS. But with that sort of lower level of seismicity, there has been several larger magnitude earthquakes that have really kind of led to significant damage in some of these rural communities around the state. So the highlights are the 2011 magnitude 5.7 near Prague. And there's still litigation going on for all of these events, really. The September 2016 magnitude 5.8 near Pawnee, Oklahoma, which we continue to study, and the November 2016 magnitude 5.0 near Cushing. And a lot of these earthquakes led to damage on the order of tens of millions of dollars, probably cumulatively statewide. But when you destroy a historic building in a rural downtown, usually that building is not going to get rebuilt due to the economics, out of the control of anybody really, affecting various rural communities. But that is still a sort of scar in those communities from these large earthquakes. And what the scientific community now understands is that the earthquakes, the larger events, were largely attributable to wastewater disposal. So the most uncomfortable time for a seismologist is when you tell somebody what you do for a living, and then as the dentist is like, in your mouth, they say, oh, it's the fracking, right? And no, well, by and large, yes, fracking is part of that ecosystem. So a lot of north central Oklahoma would not be economic. The Mississippi line would not be economic without horizontal drilling and hydraulic fracturing. But once that well is fracked and brought online, that production well, the wastewater that comes out of that formation, and in some cases, it can be 90% produced water, for example, in the height of the Mississippi line production in 2014, 2015, that water needs to be economically dealt with. And the most economic way to deal with that wastewater, those very salty brines, is to pump it deep underground into good storage formations. Now in Oklahoma, the storage formation that was most popular was, of course, the Arbuckle group of rocks directly overlying the basement. And you can see these rocks if you're driving down I-35 south of Oklahoma City. You can see those as they've been sort of, there's, collisional tectonics in the southern Oklahoma has led to those, being exhumed and being visible as you're driving by I-35. Now, we put together, and this is a sort of dashboard that sort of shows the sort of statewide disposal in the area of interest that the Oklahoma Corporation Commission has designated their area of interest for tracking Arbuckle disposal volumes. And you can see that over time, as Arbuckle disposal increased, there was a concurrent, although maybe shifted by a lag of a couple of years or so, increase in the seismicity rate statewide as well. 2011, you can see late 2011, there's a Prague earthquake. but these are pretty closely mimicking one another. The Arbuckle volumes go up, the seismicity rate, lagging again a couple of years, goes up, and then as those volumes decrease, the seismicity rate has concurrently decreased as well. So that's just a closer view of that for those in the back of the room. But as we've declined and we're down to Arbuckle volumes that are well below, pre-2009 Arbuckle disposal volumes, you can see that there is some level of ongoing seismicity that's greater than this magnitude 3.0 or greater. So we still have, frequently experiencing earthquakes that are widely felt in a lot of areas of the state. Now, one of the initial lessons learned from researchers sort of aggregating evidence from not just Oklahoma, but Texas and various other places around the mid-continent, is that when you have high volume disposal, so high rates, and this is tracking now, the way to read this plot is that once you exceed this 10 to the 5 value here, so that's about 100,000 barrels per month, the well, now this is tracking every single well in the sort of mid-continent and trying to identify whether there's seismicity within a certain radius from that well. So once you exceed that 100,000 barrel per month threshold, you're more likely to have earthquakes associated with that well than the statistical average. Okay, so that tells you, right, and then that sort of doesn't exactly hold for a cumulative injected volume. So there's some sort of, rate of subsurface injection is leading to some of these earthquakes. Now, this doesn't explain, of course, all the events. And one of the caveats that I like to point out is that this is not exactly directly applicable to all regions. So what I mean to show in this picture, this is the earthquake density just in the last year. And you can see the red spots are just areas where there's a cluster of numbers of earthquakes, higher density of numbers of earthquakes. And then on the right-hand side of the plot, you have the mean monthly injection over the last year too. So you can see that there's relatively high injection in northwestern Oklahoma, but actually these earthquake clusters, also in northwestern Oklahoma, are not necessarily clustered adjacent to or directly on top of those high water volumes. And then also you see that there are hotspots of seismicity where there's comparatively little injection compared to some of the highest volume injectors. So we understand that, in order to better understand induced seismicity, there are all kinds of nuances to this sort of mechanisms by which we might, try to, forecast where the seismicity is going to occur. And this is partly, due to the fact that there are other mechanisms for inducing earthquakes. So the sort of common model that we had, conception that we had prior to Oklahoma providing this inconvenient evidence was that you simply had some sort of reservoir that you're stimulating. For example, this is an example on the left-hand side of some sort of cartoon where there's a geothermal stimulation. You have a fault at depth, and this geothermal stimulation can cause stresses that might promote fault failure right there, okay? And I just want you to notice the different length scales too. So this is about a kilometer here for this illustration. And then on the right-hand side, you have what we now understand is that there are collections of high volume injection wells into a sort of, high permeability formation that may transmit pore pressures laterally. And with those pore pressures come pore elastic stresses, which then can also promote fault slip activity on the order of 10 kilometers away. So of course, we had to have these high volume injection wells and these clusters of high volume injection wells in Oklahoma to better understand this mechanism. And pore elastic stress is just the fact that if you increase pore pressure in a discrete zone, you're actually going to push on the rock matrix at a sort of time scale that's faster than the ability of that water to diffuse through the pore spaces. So you can have pore elastic stresses and pore pressure effects from the same injection points. And that's just to tell you that the science is complex to understand. Now, I talked before and said, told you that fracking was part of that ecosystem, right? When we think about sort of the wastewater disposal, case history of the last decade in Oklahoma, I sort of glossed over the fact that, fracking is a component of that. But of course, fracking does produce small earthquakes. And, getting ahead of the issue, the Oklahoma Corporation Commission instituted a stoplight protocol. So that means that there are, various levels of economic disincentives for operators to produce felt seismicity. So that, all the way leading up to sort of, if you are, producing magnitude, reaching up to 2.5, the Corporation Commission is gonna reach out to you, and they're gonna scare you with the, possibility of having a pause in your operations, which, comes at, if you're having a service company fracking your well, that comes at an economic cost to producing that well, of course. So you don't want to institute a pause. And so you're disincentivizing making larger and larger earthquakes that are going to be felt by people. And so when we track the sort of fracking related seismicity, we find that a lot of the seismicity clusters in this sort of scoop stack area, which is west and northwest of Oklahoma, west and southwest of Oklahoma City. And some of these events are felt, but when we track this over time, we find that the felt earthquakes are declining over time. So this is a pretty busy plot, so I'll walk you through it, but on the left y-axis here, we have well completions per month. So this is an indicator of how many completions across the state are occurring every month. And you can see that it increases through time up until it starts to decline right before COVID hits. So early 2020, completions are almost going to zero. And then you can see over time, into 2022, that they're steadily increasing, but we're nowhere near the level of completions that we were experiencing per month in 2017, 2018. Now the red bars here are the number of completions associated with a magnitude 2.5 or greater earthquake. And so you can see that while we had a number of completions associated with those larger felt earthquakes, that it's declined pretty significantly in the last 3 years. Of course, there's a component of those completions actually, the number of completions is going down, and so maybe they're not interacting with different faults. It's hard to tell from this broad sort of bird's eye view meta-analysis. But there's also a reason to be relatively confident that these completions are going on just without producing the larger earthquakes, because we can see that the number of any types of earthquakes that are associated with these completions are still relatively high. So in a way, industry has gotten better at reducing the number of felt earthquakes. So I think in some ways this is a success story. So some of the lessons from mitigating induced seismicity are that, the high volume disposal is going to promote seismicity, so best to keep the volumes low. Proximity to faults is important. Studying the geology is important. Studying the structural components that produce faults in the subsurface and whether those faults are oriented in a way that's going to slip is important. I didn't show this, but you can see on our poster over there that actually when the Corporation Commission has gone in and rapidly shut in disposal wells, we've shown statistically that reduces the aftershock activity and thus maybe reduces the seismic hazard. And then these long-term regional reductions in wastewater disposal, driven by market and regulatory factors, have led to a decrease overall. I showed you that decrease over the last several years. And then I think also that the traffic light is showing that it's effective at disincentivizing well completion seismicity. Now, this is a plot that's showing that same plot you saw before with the seismicity and Arbuckle disposal. And then on the bottom, these are EIA numbers for produced oil and produced gas from the state of Oklahoma. So these additional regulatory constraints have not impacted industry's ability to produce from Oklahoma oil and gas fields, which, as many of you know, are sort of direct indicators of the state of financial health for the state government. So this is exciting news. Now, We're mostly, so we are a university department, so we have, externally funded projects, DOE, NSF, and the like. But a lot of what we do is this sort of real-time, network monitoring. And we operate over 90 stations around the state. And even to this day, we record about 15 to 20 earthquakes per day associated with well completions, again, west of Oklahoma City, and still ongoing effects of wastewater disposal in northern Oklahoma. And, when we talk about the sort of the future of how these, state agencies are going to, cope with the sort of problem of large scale distributed carbon storage, we really need to leverage, some of these emerging technologies like machine learning, the ability to have smaller sensor packages and more of them as the economy of scale is built into these things, and we can get more of these more cheaply and connected in real time to our systems. And we need in situ measurements. So this is an example of relative pressures from some shut-in Arbuckle wells that the survey has led in the past. This is an example of leveraging deep learning neural networks to actually detect earthquakes that we hadn't been able to detect previously. So we've implemented this into our sort of real-time processing, and we're able to detect a factor of 2 more earthquakes than we would have been able to detect with our real-time system, real-time earthquake processing system. And this is an open source software package that we've released into the community, is being used already by researchers around the world. So I just use that as a way to show that we've integrated this into our real-time systems and into our sort of routine systems, but also there's a real research endeavor that I think is largely unexplored and which needs to be explored in order to also help agencies understand microseismicity from some of these from some of these potential projects related to carbon storage. So this is an example of Eastern Oklahoma, a hotspot of seismicity that we've worked with the Corporation Commission and discussed over several years now. Particularly, there's one injection well in this area combined with a number of well completions adjacent to it. And this is the sort of view that we had from our regional network. So obviously, if you do the magic eye thing with me and squint a little bit, you can maybe convince yourself there's maybe a northeast striking fault and some sort of complementary structure to that maybe. And we've deployed these nodes. So these nodes are these small 3-component geophone packages, and there's Paul there. And you can ask him about this experiment, but there's Paul just deploying one of these nodes in the area. And you can see that we have about 30 of these small nodes off of county roads in the area because we want to better constrain that seismicity. When we do, we look at the sort of relative depths that we're getting when we're augmenting the sort of regional picks with the waveforms that we're getting from these very small earthquakes that are recorded on these nodes. And when we look at that, we actually see that there's some sort of through-going structure into the Arbuckle, rather than sort of these earthquakes being deeper down into the Precambrian basement. Now, when we apply the machine learning technology that we're leveraging, again, in sort of this routine processing for our seismic network, we see all kinds of very complicated structures. As you know, we joke sometimes that the geophysicists always see our lines on maps for faults. And if you've ever actually looked at a fault zone in the field, you know that faults are more complex than that. They contain damage zones, and they're much wider than just one line drawn right through the rock, right? So there's some sort of complex damage zone, but the sort of machine learning leverage detection is showing that extends from the basement up into the Arbuckle and all the way through up into the Simpson at least. And this it's important to note this injection well is actually permitted for the Simpson. And so, providing that evidence to the Oklahoma Corporation Commission is going to give them, the best evidence to make their sort of regulatory decisions, which again impacts, the operators, but it also impacts the people that live in these communities that are experiencing this shaking too. So there's an important sort of nexus of sort of public understanding, science communication, and then action that the public feels is ensuring, the safety for again, for these projects that are going on in the subsurface, which, people, the general public just doesn't generally understand in great detail. So I'll sort of, start to wind up here with a sort of vision of what this could look like in the future. So we'll talk about the numbers in a little bit here, but understand that the Oklahoma Corporation Commission is an agency that has under their purview something on the order of 14,000 Class 2 wells. Now, I think that, really realistically, in order to get to the gigaton scale types of numbers that you need for carbon storage to actually make a dent into just the US emissions, let alone considering global emissions that are occurring every single year, you actually need these programs to be envisioned on a broad scale, much like the footprint of, these wells that exist in places like Oklahoma across the US. And so let's consider this sort of thought experiment real quickly here. So if you look at sort of the Arbuckle injection history, and you do the sort of back of the envelope, anybody can check my math if you want, but you do this thought experiment, and you consider that supercritical CO2 is about 700 kilograms per meter cube. You can actually get a quick estimate. Okay, so if we sort of thought that this saltwater brines that is being disposed of is instead supercritical CO2, how much are we actually putting in the ground? So it's about at its peak. It's still only, on the order of maybe 10 megatons a month at the peak of injection and the peak of seismicity. Okay. And then so cumulatively, this program would have in the last decade would have only injected and stored, and you can argue if we've safely stored it or whether the sort of CO2 is going to be stable within carbonate rocks of the Arbuckle. That's another sort of conversation that I don't really have the expertise to help you out with. But we've only cumulatively sort of, stored on the order of 700 megatons. Now, understand that every year we emit on the order of 5 gigatons of CO2 in the US. So obviously, carbon storage is going to be one component of the solution for mitigating, again, climate change, if that's the goal that we're setting for ourselves. We're not in a position to sort of, argue the merits of that, whether or not, that's a goal we want to sort of achieve. But I think that there is the capacity to do this, because we also have some in situ measurements that suggest that there is storage capacity still in the Arbuckle. So this is a program whereby a lot of these shut-in wells were sort of just instrumented with these pressure transducers, which is recording the relative head in each of these wells over time for about on the order of 3.5 years or so. And where in a lot of cases, the wells that we've instrumented, these Arbuckle disposal wells that were shut in again, a lot of these wells were suggesting that there were declines in the head such that there is a lot of storage capacity still left in the Arbuckle. Whether the Arbuckle is going to be a suitable formation in the future for Oklahoma for carbon storage, long-term carbon storage, I hope that Ming this afternoon will give us some answers about that. So in summary, I think that, again, the sort of the way in which I sort of, wanted to talk about these things was, what are some broad sweeping lessons from the Oklahoma situation that we could apply for regional carbon storage management from the perspective of seismicity? And I think that, understanding that the volume is important, not just from single wells, but collections of nearby wells. Learning something about the subsurface is incredibly important. So doing that sort of site planning ahead of time is important. There are some tools for rapid mitigation that I sort of highlighted, discussed, and I can talk more about those at the poster later today. But I think, in a lot of ways, there's the, again, that component that happens outside of this room, right? The sort of science communication, the the making sure that that social license to operate, it stays intact, and creating those ties amongst the communities. So that's a science education component, not just at the higher education levels, but K through 12. That's a sort of public messaging component of that. And I think, really, in some ways, the State Geological Survey is not just at Oklahoma. I'm envisioning this as a blueprint for other state agencies, but I think state surveys are uniquely positioned to do this and to handle some of these things. And obviously, there needs to be a trusted relationship between the state agencies, the public, and industry as well, in order to make sure that is realized, that vision is realized. And I think leveraging some of these emerging technologies with some investment is also going to be the last kind of final step towards getting there.